Okay, so after introducing so-called the divergence operator and also the curl operators, now we like to show two algorithms. Okay, let's know two algorithms. Sorry, two theorem to actually show the equivalence between the integration form and the differential form. Okay, so so the divergence theorem is like, or we can also call it the Gauss theorem. Okay, you can simply imagine this Gauss theorem will be useful for, or actually related to the Gauss law. Okay, so here it says for f is a vector field. Okay, we have this surface integral equals the divergence of f, and then take the triple integral over the volume. OK， 所以中文的意思是，如果这个 f 是一个向量场，我们找一个面，找一个 s， 找这个 s 这个是一个，你可以想象它是一个高斯面的 s， 对于 s 这个面去做面积分，它会等于这个 v， 这个 v 就是被这个 s 所包围的这个体积，对于这个体积做这个 triple integral 就是积分这个体积。那但是它不是单纯积分它自己，而是要积分这个 divergence of f，divergence of f。OK， 所以这个是二重积分，这个是一个二重积分，这个是这个三重积分，但是这里有一个 divergence， 你可以看成这个是一个导数，它一个类似导数的东西，那这里要做3次积分，那这个只做2次积分，它们是等效的。它其实也是另外一个是那个fundamental theorem of calculus， 就是微积分基本定理的另外一个高维度的形式。最简单的那个形式就是导数跟积分它是逆运算的关系最一开始学微积分的时候，你会学到这个 fundamental theorem of calculus in one dimension， 就是一维的是那样。那这个是2维、3维的是这样。那你可以看成这个是2个积分3个积分，但是做一个导数，所以对所以就是多做一个导数，那你就多做一个积分，它们就等效。Okay, so it says the surface integral of a vector field over the boundary of the volume equals to the volume integral of the divergence of the vector field over the volume. OK， 所以我们不会去证明这个定理，因为这个是无微积分怎么说多变数微积分的一个课程，我们不会去证明。有兴趣的话可以看一下，它好像是4、5页的去证明这个 divergence theorem。那它的物理意义是什么？它的物理意义是说，如果我们要做这个面积分的话，我们另外一个的话就是我们尝试去把这个 这个 f field 这个 f 这个向量的场去做梯度，梯度完之后，对于它这个体积里面的每一个点，它都会去找这个 divergence。找 divergence 的话，就相当于对于这个点，我去看它是流出流入，然后每一个隔壁的点，它也会去找一个 divergence 流出或者流入。那它的意义是说，如果它们相邻的话，它一个是指这个方向，这个是指这个方向，它们就会互相抵消。所以它在里面整个体积里面，它都会抵消，只剩下表面的部分它没有办法抵消。那剩下表面的部分，它就会变成这个面积分。当然讲起来很抽象，但是具体的数学证明的话，就看到这个连接。至少好像前1、2年的话，它还在存在的。我觉得应该，它应该还在存在我猜它应该还是存在的这个连接。OK， 所以 物理的意义大概是这样，如果你理解不能的话，就是你相信它是正确的啊。OK， 那另外一个叫做 Stokes theorem 啊 ，Stokes theorem。OK， 叫做 Stokes theorem。OK， 那 Stokes theorem 的话，就是说现在 F 也是一个for F is a vector field。Okay, so it will satisfy, or this is the line integral. This is the line integral. Okay, and then this contour, or this loop is called round segment. Okay, so this is round segment. And then for the sigma is actually the surface enclosed by this contour. So this is the surface integration for the sigma. Okay, so on the left side, this is the line integral of f through this path. Okay, round sigma. And then on the right side, it is the curl of f. The curl of f. After taking the curl of f, we can do the surface integration over this surface. Okay, 所以它是这个意思，就是the line integral of a vector field over the boundary of the surface equals the surface integral of the curl of the vector field over that surface. 所以它的物理意义也是类似的，就是说，如果我们有一个 vector field f，我们在这个整个面上面每一个点都找这个旋度，就比如说我这个点找一个旋度，我隔壁那个点也找一个旋度。那这样的话，相邻两个点的旋度一个就是往上，一个往上它们总是会相反的，就会互相抵消。反正它们有相邻的，它们都会互相抵消。那剩下的话，只剩下最边缘的部分，它会保留下来，没有办法跟其他人跟它抵消。所以最后剩下来的话，就是这个 f 的线积分而这个旋度，整个面积的旋度内部全部都会消耗殆尽Okay, so this is the physical insight. Okay, for this Stokes theorem. And if you would like to be interested about the rigorous math, okay, you can check this link out. 那这个 Stokes 的话，它就有一些物理的故事在背后那 Stokes theorem 的话，就是说他当时是一个大学教授所以他当时在一个大学里面有一个考试，他就当时也碰巧他想出这个 Stokes theorem， 然后他在那个考试的时候，他就出了这个证明题，叫人去证明这个 Stokes theorem 我不知道是什么出于什么动机是不是为了展示他很厉害但是这个考试的结果是所有人都不会证明，只有一个人证明出来，那个人就是 Maxwell 就是 Maxwell。所以最后的话 ，Maxwell 也用这个 Stokes theorem 去搞出这个Maxwell equation 一部分的那个微分形式所以这有一个物理的故事在背后这个 Stokes 跟那个 Maxwell。Okay, so here we try to accept these two theorem is correct. If you don't believe, so try to persuade yourself these two theorem are correct. Okay, so here we try to derive the differential form of the Maxwell equation from its integration form. Okay, so we start from the Gauss law for the electricity. So first one, okay, we already rewrite the Gauss law to be like this is the surface integral, and then on the right side is the triple integral of the volume charge density over this epsilon naught. Okay, by applying the divergence theorem, okay, so we substitute this f to be E. Okay, we substitute this f to be E. So this is E, this is divergence of E. Okay, and then it will be like that. This is the surface integral of E. Okay, which means this one will be the same as this one, and then we will change it to this one, which is the triple integral of divergence of E. Okay, so this is what we need. Okay, so here we try to put this one to here. Okay, so which means this one will go to here. So we have a triple integral of divergence of E dv. And then on the right side it is still the same, but we try to put this 1 over epsilon naught into this triple integral. Okay, so this is a constant, so it doesn't change anything. So we have a triple integral of rho over epsilon naught dv. Okay, so here, okay, on both sides we have a triple integral of dv for the same volume, but this will be true for any given volume, which means the integrand itself should be the same. Okay， 因为本来的话就是两个积分相等，那里面相等的话，其实你要小心，就是如果是一维的话，因为你定积分的话，它会有一个加 c 的存在，但是这里的积分的话，它不会有那个不定积分的那个应该说不定积分的那个加 c， 所以它们两个会相等。而且相等的条件是因为这个三重积分，它对于任意的体积，它都要相等，所以它必须要里面这个线是相等的，它才可以保证这两个三重积分在任意体积之下都相等。So we have this divergence of E equals rho over epsilon naught. Okay, so this is actually the differential form for the Gauss law for electricity. And similarly, we can repeat the same procedure for the Gauss law for magnetism. Okay, so the only difference is that on the right side it is all the way 0. So on the left side it becomes this one, and then on the right side it's nothing but 0. So we have this one. So this is also the 2, and so these two are the two Gauss law in differential form. Okay, so this is easier. For the Faraday's law, okay, so we have already rewrite it like this. So we have a line integral of E field. So this is the induced E field, and on the right side ddt for the phi b, and then we already rewrite phi b into this surface integral. Okay, so here we reapply the Stokes theorem. Okay, Stokes theorem, we replace F vector to be this E vector. Okay, so this is the line integral, and then this is the surface integral, but for this curl of E, So in this case, we have so we have this side. This side is actually the same as this induced E field. So we just put this one to there. So which means that we have this one to here, which is equal to this one. Okay, we equal to this one, put it here. And then here we try to put this one into the integral side. But we need to change this derivative. Okay, the ordinary derivative into this partial derivative. Okay, so we have a partial b partial t inside this double integral. And then similarly, as much as this double integral and this double integral are the same for arbitrary surface. Okay, so which means the integrand itself should be the same. So we have a integrand on the left side, which is curl of E to be negative partial b partial t. So this will be the differential form for the Faraday's law. And then finally, we also can derive the differential form for the Ampere's law. So this is the Ampere's law. On the left side is the induced B field. So for the first term is from the static current. Okay, so which is already mu 0 I enclosed. But we rewrite the I enclosed into a double integral, or the surface integral of the current density. Okay, of the current density. And then for the second term, which is related to the displacement current. Okay, displacement current should be epsilon naught d phi e dt here. Okay, but we also rewrite this phi e into a surface integral of E field. Okay, so here we also try to apply the Stokes theorem here. So we have a line integral of BDS is actually the surface integral of curl B. Okay, so similarly, this one and this one is the same, so we just put this one to there. So which means this one go to here, and on the right side, we try to put mu0 inside, and then we also try to combine these two double integral together, because these two double integral is applied for the same surface. Okay, so we can just combine them together. So finally, we have a mu0 j, mu0 j, and then we also have this epsilon naught plus partial e partial t. We also try to put this one inside. Okay, so we have an epsilon naught partial e partial t like this, and then mu0 multiplied by a j plus epsilon naught partial e partial t to be here inside this double integral. So on the both sides, we have this one and this one. Okay, both of them apply for the surface integral for the same surface. So that according to the same argument, the two integrants should be the same. So which means the curl of B should be mu0 j plus epsilon naught partial e partial t like this. So this is the differential form for the Ampere's law. So in such a way, we have already used the divergence theorem and the Stokes theorem to show the equivalence between the integration form of the Maxwell equation and the differential form of the Maxwell equation. So this is nothing but this. Okay. So on the left side is the integration form, and on the right side is the differential form. Okay. So finally, we would like to show that in chapter 32, we mentioned that we need to add this displacement current so that the Ampere's law will be more complete. Okay, it not only covers the static current to generate B field, but also covers the displacement current to also induce B field. Maybe you have a question whether we have the third stuff which can also induce B field. The answer is no. Okay, because up till now it should satisfy the conservation of charge. Okay, so this one should be like divergence of J. Okay, not gradient of J. Okay, so here we would like to show this one. This one is actually the conservation of charge. Okay. Okay. So first of all, we have a rho to be the charge, Coulomb charge density as before, and then the J is the current density. So in this case, we have I equals negative surface integral of J, dA. Okay. In the textbook, we doesn't care about the direction, but here we really care about, because we would like to have a closed surface. Okay, a closed surface. This is a closed surface. We would like to consider the rho inside, and also the Q enclosed inside this closed surface. 我们关心的话是一个封闭的曲面里面所包含的所有的 Q enclosed 因为跟这个高缩有关，或者是跟这个电流有关，应该是跟这个电荷跟这个电流有关。所以它的意思是，如果它有一个电流的话，它是这个 JDA 然后负号 JDA 然后负号，这意思是说本来这个 surface integral 我们会定义这个 J 是流出是为正的，流出是为正的，但是我们取个相反我们这个 I 是 ，I 是往内的，I 是往内的，因为等于说我如果是 I 往内的话，I 往内的话，它的电荷密度会提升，我 I 往内的话，我里面的电荷密度会提升，所以这里有多一个负号，本来的话它不是封闭曲面，所以正负号就无所谓，但是这里的话是一个封闭曲面，所以我们要关心这个负号。Okay, and then similarly, we also apply the Stokes, I mean the Gauss theorem or the divergence theorem for this side. Okay, so this surface integral becomes a triple integral, but with the divergence of J here, and then we also put this negative sign inside. So we have a triple integral of this negative divergence of J to be the I. Okay. And then similarly, we can have, according to the definition, I mean for the definition, we have I equals dq dt. Okay, this is the definition for the current. And then the Q will be the triple integral of the rho. Okay, just like what we did for the Gauss law. Okay, so Q will be the volume integration for the volume charge density. Okay, so in that case, we also try to put this ddt inside the triple integral, so that it becomes a partial derivative. Okay, so here, this is I, so they are equal to each other. So which means that this I equals to this stuff, and this I equal to this stuff. So which means this one is equal to this one. So we put this one here and that one there. Okay. And according to the similar argument, if these two triple integrals for the same volume are the same, so the integrand should be the same, which means this partial rho partial t, this partial rho partial t should be negative divergence of j. Okay, divergence of j. So this one, okay, or if we put this one on the left side, which will be partial rho partial t plus gradient of j, and then this is called the conservation of charge. 这个是电荷守恒的一个数学的式子这个数学的式子就告诉你说这个是电荷守恒。电荷守恒的意思在这里的物理意义的是说，如果某一个地方它的电荷密度随着时间改变，就是这个 partial rho partial t。如果它是增加的话，就表示说它有一些电流流进来，应该是流出了，或者是以这个来看的话，就是说，如果这个电荷密度对于时间来说是增加的话，那这个的话。如果是 divergence of j 没有这个负号的话，正的话是流出嘛，但是它是流入它的电荷密度才会增加，所以再有一个负号。如果这个电荷密度是减少的话，那应该是有一个东西是，就是那个电或者是这个电流密度是往外的话，那这个是负的那就是这个是一个，那这个就会是一个正数这个是一个正数，那整个就会是一个负数。OK， 所以这个是一个电荷守恒的式子，所以这个意思是说，这个是电荷守恒的式子。那实际上现在的这个 Ampere's law 跟或者是 Maxwell equation。这状态之下，它就会跟这个它就会跟这个 convergence conservation of charge 是相容的Okay, so here we try to take the divergence of the Ampere's law. Okay, originally the Ampere's law is like this part, and also without the divergence part. Okay, but here we try to apply the divergence to the Ampere's law. Originally, the Ampere's law is like the curl of B. The curl of B is mu0 j plus epsilon naught partial e partial t like this. This is the Ampere's law, and then we try to take the divergence on both sides, and then you can, actually you can check it on the Wikipedia. We have an identity called the divergence of a curve is always a zero. 就是它如果又散又旋的话，它一定是零。如果你想要一个更严格的数学证明的话，你可以自己去拿前面的那个Cartesian coordinate 的那个梯度旋度，你算一个 f 的话，它算出来它一定是零，因为它对完两个东西都算完之后，它一定会消失不见的，它一定会消失不见，全部都会归零的。OK， 所以我们用的这个式子的话，就是左边为零，右手边剩下什么 ？OK， so by Gauss law, here we have the divergence of E here. Okay, so which means it becomes rho over epsilon naught, rho over epsilon naught. Okay, so it becomes partial rho, partial t, and then epsilon naught and over epsilon naught cancels. So here it remains partial rho, partial t, and then here is still divergence of j. Okay, so here we have 0, which is from this part, equals mu0, divergence of j plus partial rho, partial t. And mu0 is not 0, so that we can cancel it, and then finally it becomes partial rho, partial t plus divergence of j equals 0. 所以这个意思就是说，现在这个 Maxwell equation，这个 Ampere's law 这个形态的话，它会跟电荷守恒是匹配的，它会跟匹配的。如果你再加第三、第四项的话，它就会不满足这个电荷守恒，那就不对了啊。所以这个是告诉你说，这个 Ampere's law 考虑了这个 Maxwell's law 之后，它就是最终的形态，它不应该再加第其他的东西去修正它啊，因为它已经最正确了。